Excellent. We're up and running. Thank you, Martin, or Dominik, for agreeing to give this seminar. Dominik Rist is speaking to us from Edinburgh. He's going to tell us about non-abelian gerbes and with connections. I'm very much looking forward to learning about this subject. I will hand over to you, Dominik.
Thank you very much. Thank you very much to Benjo and the rest of the people for inviting me to give this seminar. It's my first time in Ireland virtually.
We must have you visit officially sometime.
Okay, perfect. Apologies if the internet connection is not the best. I mean, today has been kind of the weather has not been the nicest here, and I think that affects the internet connection at my place. So apologies if please do interrupt if you have questions or you want something repeated or anything on the technical side. Okay, so I'll be talking about my work with Christian and Martin that I did during my PhD at Heriot-Watt University. The work has been concerning with non-abelian gerbes with connections. And in my talk, I'll basically describe the construction of and definition of non-abelian gerbes with connections, and also provide some basic examples, some basic non-trivial examples of such. Okay, so the motivation comes from basically physics, as always for us mathematical physicists. So we want to understand gauge theories and higher gauge theories better. Why? Because gauge fields are everywhere. So we can find them in Standard Model, Yang-Mills theory, Chern-Simons matter theories, which have important applications also in M theory, in particular the BLG and the ABJM models, or the so-called M2 brane models. So these are mainly ordinary gauge theories. So we are working with a connection on an ordinary principal bundle, and this is the geometric framework that we use to formulate such theories. Then we also have some higher forms appearing in string theory, such as the Kalb Ramond B-field, which is very well known, or the B-field in heterotic supergravity, and a whole tower of higher form fields appearing in tensor hierarchies in gauged supergravities. And we would like to interpret these fields just as we did for one form fields appearing in ordinary gauge theories. We would like to interpret these higher form fields as some higher connections in higher gauge theories on some higher principal bundles. For me, the main motivation comes from the study of M5 brane models. So what are those? First of all, we need to understand what is M theory. We don't understand what is M theory. We just know that it's this mysterious unification of the 5 consistent superstring theories. And in M theory, the interesting objects that appear are M2 and M5 branes, which are dynamically interacting objects. Not much is known about their dynamics. I mentioned the M2 brane models, which are known, but for M5 branes, the situation is much less understood. Okay, and there is a theory called the 2-0 theory, which arises on M5 branes, on the world volume of M5 branes, when they interact via M2 branes. So this is a 6-dimensional superconformal theory with a 2-0 supersymmetry. This is the setup, how you should imagine it. So you have a stack of M5 branes interacting via M2 branes, and the fluctuations of these M2 branes, of their boundaries, the M2 branes, they induce certain fields, so-called 2-0 tensor multiplet, which includes a two-form B-field, which satisfies a so-called self-duality equation, right? So this is a higher version of an instanton. Here it's written. Okay, so I'll use this. Wait, this is the equation, the self-duality equation that the B-field obeys.
Sorry, could I just ask a question quickly?
Yeah.
What do you mean by 2-0 SUSY?
You have the 2-0 n equals 2-0 supersymmetry. So it's chiral and n is equal to 2.
Okay, thank you.
So it's in 6 dimensions. You are in 6 dimensions. So you are looking at the representation theory of the superconformal group in 6 dimensions. And this is one of the possibilities that you can have. Okay. So you have the 2-0 tensor multiplet, which includes the two-form B field, and you have some other fields in it as well, such as 5 scalars and some Weil spinors. And okay, but we'll be interested in this B field and understanding how to interpret this geometrically. So this is just the motivation. Okay. Oh, no. Right. So we know that mathematically ordinary gauge theory with one-form gauge fields is described using principal bundles with connections. What about higher form gauge fields? So we need a framework to go beyond connections on principal bundles and a framework to describe parallel transport of extended objects. Because just as connections give you parallel transport of point particles, right? If you want to understand how the wave function of a particle transported along a line is affected, you only need to use the framework of ordinary gauge theory and ordinary connections on ordinary principal bundles. However, if you want to do the same thing with extended objects such as one-dimensional strings or two-dimensional branes and so on, you need to go higher. Okay.
Sorry, just another clarifying question. When you say instanton, could you just clarify?
You mean here? Yes. So yeah. I mean the ordinary instantons, they are self-dual configurations of Yang-Mills field, right? So you have the curvature F, which is basically just dA or dA plus 1/2 the commutator of AA, where A is your connection, and F equals Hodge F is the instanton equation, right? It's the self-duality equation. So in this version, you are working with a two-form and its associated three-form curvature. So this is like a higher version of an instanton. These configurations, by the way, are called self-dual strings.
So are these instantons different to the instantons I'd see in tunneling problems in quantum field theory?
Right. So, well, these higher versions, I'm not sure I'm not sure about this interpretation in terms of tunneling in this higher case, but they should be analogous to that situation.
So there are a vacuum in this field in this setup that I can tunnel between.
Essentially, yes. Essentially, I would guess so. Yeah.
Yeah. So I don't have much of a background in string theory, so this is quite new.
Okay. Yeah. I mean, yeah. So we are just interested in understanding how to interpret this geometrically. The actual QFT properties of these objects are still unknown of self-dual strings, but yeah, I'll get to it later on in the later part of my talk. So let's just go to the framework of higher gauge theory. So higher means categorified. We'll be using categories and higher categories, so we need to understand what are those. So I'll try to be fairly pedagogical here. So I'll recall elements of categories and two categories in case some of you have not seen them. Then I'll provide the definition of a principal bundle via this categorical perspective, so via cocycles in this case. Then I'll comment on how to describe locally connections via objects called L-infinity algebras. So these will be higher versions of differential graded Lie algebras. Okay, then this, if we have the local description, then we can try to glue the local pieces together into a global picture, and what that will provide us will be the global cocycle description of gerbes. So gerbes, I'll understand as principal two bundles. You'll see what precisely I mean by that later on. And depending on how much time I have, I'll also describe a particular example of a higher of a non-abelian gerbe with connection, namely a string 4 bundle over S4. So I'll define what a string group is, and I'll describe this example in quite some detail, depending on the time, of course. Okay, so let's get into it. So categories, higher structures, and all that. So let's recall what are categories. So a category just is a collection of objects and collections of arrows or morphisms between these objects. In particular, you can imagine just a picture like this. So A, B, and C are my objects. We have the identity morphisms, which are these arrows. And we also have arrows between different objects that we can compose. The composition is a functor, so it's a, I need to move. Okay, and not all maps, of course, can be composed. Only those for which the target of one agrees with the source of the other, right? Then I can compose two maps. What are source and target? I mean, as the name suggests, source of an arrow is basically where the arrow starts, and the target of the arrow is where the arrow points. So these are the two maps that I have associated with a category, and this motivates the following notation that I'll use for categories. Here it is. So C0 is my collection of objects, and C1 is my collection of morphisms. And this double arrow notation just means that I have the source and target maps in this category. Okay, so this kind of setup fully specifies a category for you. So this is what I'll mean and what I'll use. This is very easy. So just a collection of objects, collection of morphisms which can be composed and which have also identity morphisms and so on. Right? When all the arrows are invertible, so when I can compose an arrow with its inverse and get the identity arrow, that means I have a groupoid. So it's how is this related to a group? Well, basically group can be understood just as a one object groupoid. So you have a category with one object, and all the group information is contained in the morphisms, and the composition of morphisms corresponds to a group product. Okay, so if I have a group, I can view a group as a groupoid, as a one object groupoid. I use this notation, BG, the delooping of G. So this is my one object. This is the group G, which means it sits where the morphisms sit, and these are my double arrows, so source and target. So this is a very trivial example, but it'll be important that I'm able to embed ordinary groups into groupoids. Okay.
Sorry, Dominik,
yes.
could you maybe clarify the notation?
Yeah, which part?
Yeah. Well, the double arrow bit. So
yeah, so the double arrow just denotes the source and target maps. One arrow is the source and the other arrow is the target.
okay.
That's all it means.
Okay, so and then what is the reason why they go this way or the other way? Is it where you have your source and where you have your target?
Yeah, exactly. It's just to distinguish the objects from the morphisms. So where they point is the objects, and where they point from is the morphisms. So that's the only reason.
And that means the same thing here in the groupoid notation?
Sorry?
So in the groupoid notation.
Here?
No, at the bottom for BG.
Okay. Yeah. So this is my one object.
Yeah.
So this is the collection, this is C0, and this is C1.
I see, okay.
Right, so these are my morphisms. So if I draw it like this, this is my group. So this is my one object, and here I have group elements G1, G2, and composition basically amounts to group product.
Yeah, okay, thank you.
You're welcome.
Sorry, just
next. What is the definition of that the morphisms are incompatible?
Right, good question. So that means that there is another morphism. Let me actually use the one that does not vanish. So I have an object A. What's going on? Okay, this doesn't seem to work.
Yes, it stopped. Doesn't work.
Yeah, okay, so let's try to do it like this. It means that I have an inverse. So if I have arrow F, I have an F inverse from B to A, such that when I compose them, this is the identity.
I see. Okay, thank you.
Okay, so this is all that is meant by invertibility. So when all the arrows are invertible, we have a groupoid. That's the definition of a groupoid. Okay, an example of a groupoid.
Sorry, just one more question. Would you expect the rules of like group theory to apply here? Would I have closure, associativity of these things?
Yes, exactly. You would have that because so there are some extra hidden axioms in this category that I did not mention. Okay, so there's such as the fact that the composition is associative. So this translates to associativity. And in fact, when you work out all the axioms involved in defining a category, you'll find out that in this case, this precisely defines a group for you. So there's one-to-one correspondence between one object groupoids and groups. Does it answer your question?
Yes, thank you.
Okay, so another example of a groupoid is the path groupoid, which you can imagine just you have some manifold M, you consider its points. These are the objects of your category. So the points belong to C0. And paths between these points are the morphisms. So I have a point x0, x1, and I have some path. And collection of all these points and all the paths between these points gives you a category which is called a path groupoid. So
don't you have to say that the product is not defined for all elements, all pairs of elements?
Yes, indeed.
I mean, that's the definition of a groupoid.
Yeah, sure. Yeah, product
That's
does
all you
not-
need. You don't need anything else.
Well, you need invertibility, right? You need to be
Yeah,
able-
it's a binary operation with inverses, but it's not defined for every element of every pair of elements.
So from
Sure.
starting
Yeah.
from so if I start from one group element, I can't necessarily get to another group element.
No, I mean, are you asking about the groupoid or group case?
Groupoid.
Groupoid. Yeah. No, well, I mean, it doesn't mean that between every two objects there is an arrow. That's not the case. Every object has an identity morphism, an identity arrow. That's true, but there might actually be no non-trivial morphisms in the category. So it depends. I mean, in this case of the path groupoid, depending on the manifold M. I mean, if it is some simple example, for example, like a sphere or the plane, and of course you have many paths connecting 2 points, right? So you have many distinct arrows, many distinct morphisms, but all of them can be inverted, right? All of them, I mean, you have a path with some orientation, you can just invert the orientation and you get the inverse path. You have to also describe, I mean, for this groupoid to make sense, you have to describe the composition of paths. And that is where the difficulty lies, because it turns out that when you go really technical in this, I should not be talking about ordinary paths, but the technical term is paths with sitting, well, thin homotopy classes of paths with sitting instants. That's the technical term. But I mean, let's not go there. So let's just imagine these paths between points. I can compose paths, right? Well, some of them, not all of them, of course. I can compose those that have. So if I have path 1 and path 2, gamma 2, that means gamma 1 has to end where gamma 2 starts, and then I'm able to compose them. Okay, so this defines a path groupoid for you of a manifold M, right? So this is another example. And now functors. So that's basically a lesson from nature called the Aharonov-Bohm effect, that we should care about category theory and functors. So what is the Aharonov-Bohm effect? So that basically just means that wave function of an electrically charged particle is observably affected by the electromagnetic potential. And it's the effect of Aharonov-Bohm effect is that nature associates to each path a phase, which is an element of U1. The important thing is that phases add when paths are concatenated, so when paths are composed, just as I explained in the previous slide, and they invert when paths are inverted, so we change the orientation of the path. In other words, this is an example of a functor from the path groupoid of my manifold, which is just the spacetime, to the one object groupoid B1, right? So the functor bit, I'll define that now. So a functor between categories C and D is a mapping which preserves the structure of the category. So first of all, it associates to every object every object in C, an object in D, and it associates to every morphism in C, a morphism in D, such that the identity and composition have to be preserved. And this is precisely the statement that phases add when paths are concatenated and invert when paths are inverted, and the identity, the trivial path, so the constant path, when you don't move, when you stay at the point, becomes the identity in group U1. So
sorry.
yeah.
Can I explain? Could you explain what is the object of the PM and the arrow of the so
So
factor of the PM?
Yeah. So PM is the path groupoid of M. So M is my spacetime, right?
Yes.
R13. And the P is just the path groupoid of my spacetime. So I consider, just as I explained in the previous slide, it's just all the paths between all the points.
I see.
Okay.
Okay. Yes. Thank you.
This gives me right. So nature associates to path groupoid. Well, nature gives me a holonomy functor, right? Which is a morphism from the path groupoid to B1. Okay, so this will be notation that will be appearing.
Sorry, when you said that your spacetime was 1-3, why would it not be like 1-9 or 1-10 if we're doing string theory?
So in that case, yes. In that case, it's more. I mean, in the case of Aharonov Bohm, it's 1-3. But yeah, it can be any manifold, right? It was just an example.
Okay, great.
Okay, so I mean, you can do variations on Aharonov Bohm. First of all, instead of electromagnetic field, you can consider other fields, right? Other Yang-Mills fields. So in that case, you would replace the groupoid B1 in this holonomic functor. In this holonomic functor with a BG, where G is any Lie group. So just as I explained, BG is just the one object groupoid with G sitting in the morphisms. And it turns out that the holonomy functor from the path groupoid of my spacetime, of my manifold M, into BG, it contains the same information as a connection on a, well, topologically trivial principal G bundle over M. So once again, topologically trivial principal G bundles over M are encoded, or a connection on this is encoded in holonomy functor from the path groupoid of my spacetime into BG. So this is an equivalent way of encoding a connection. So this is one variation where you change your group U1 to be a potentially non-abelian V group G. The other variation is when you try to parallel transport extended objects. So instead of considering how a particle wave function is affected by an electromagnetic field, you might consider how a string wave function is affected by some background field, by the background Kalb Ramond B-field when you move it, when you transport the string in your spacetime. So you would be interested, in this case, you'd be interested in the higher parallel transport or parallel transport of a higher dimensional surface. It doesn't have to be just string, it can be a membrane or something higher dimensional. Okay, so all of this is, I mean, in effect, the framework that's being that one needs to use here is basically higher gauge theory and higher principal bundles. I hope I've stressed that enough. But let us first view ordinary principal bundles in this framework. So let us first try to understand how principal bundles arise from functors, from this functor description. Okay, so for that, I'll be considering the cocycle description of principal bundles, which I'm sure everybody is familiar with. Right, so we know that a principal bundle can be given by listing transition functions, which are just maps from. Okay, so let's start like this. So we have a space-time M, and we cover the space-time or the manifold by patches. So UA are my patches, which cover my manifold, and on the overlaps of patches, I give you transition functions. So these are maps from the intersections of the patches into a group G, such that they obey this condition. So on triple overlaps, UA intersection with UB and intersection with UC, you get this condition. So GAB times GBC is GAC. This encodes a principal bundle, a topological principal bundle. So that means we are not talking about connections yet, just about the global structure of the principal bundle. Okay, so when you give me this is an equivalent way how to describe a principal bundle on a manifold, a principal G bundle on a manifold M, subordinate to this cover. Okay, how do you describe this in terms of functors? First of all, you construct the check groupoid. So here we have another example of a groupoid, which is constructed as follows. So you start from the cover of a manifold. The objects of this groupoid are pairs of points and indices of patches where these points belong to. Right? So for example, this notation just means that I have a point X, and the point X belongs to UA, to patch UA. Right? This is just XB, so point X belongs to patch UB, and so on. The morphisms in this category, in this check groupoid, are given by triples. So there is just one morphism between any two distinct objects, and that is XAB, right? So that's very, very trivial. I just consider the triple where X is the point and A and B are my indices. So this is very formal, that there is nothing profound happening here. So once again, my objects are points with labels of the patches to which they belong to, and the morphisms are just triples where I consider the point itself and the labels of patches between which this morphism acts. Okay, so this is all I mean by check groupoid. So how does composition look here? I mean, if you have 3 points, XA, XB, and XC, so X here is the same, right? So X belongs to the intersection of ABC. So I have these 3 distinct objects, XA, XB, and XC, but X stays the same. Then I can consider these morphisms between these objects, XAB and XBC, and the composition gives you a third morphism, XAC. So this is how I compose in a check groupoid. The inverse of every morphism, for example, XAB, the inverse of that is just XBA, right? So very simple. And the identity morphism is just XAA. So yeah, it's all trivial.
So the
And-
definition of the check groupoid is a groupoid in which there is a point X that belongs to different patches.
Yes. Yeah, I mean, so if you want to be able to talk about these arrows, you have to have non-empty intersections, right?
Yes.
So the intersections have to be non-empty in order to be,
Yeah.
yeah.
Yeah, for it to be a check groupoid. Got it. Thank
Yes.
you.
Right, so this is my check groupoid here. The objects are just as I explained, points like, well, points of this form, and the intersections are here. And the functor, just as I explained, is given by these two arrows into BG, right? What was BG? Using the notation from before, BG was the one object groupoid. So I have a single object and the group G sits here in the morphisms. And it turns out that this functor contains precisely the same information as the transition functions, including the cocycle condition of transition functions. So that's very easy to see because I said that functors preserve composition of arrows, right? So if I compose, for example, these two arrows, each arrow is mapped by G, by this part of the functor, to some element G AB X in G. Sorry, that was gone quickly. So this is what I obtain. And the composition, the fact that functor preserves composition of morphisms in my check groupoid just means that I obtain this condition, this cocycle condition on functions GAB, right? So we indeed see that functors from the check groupoid into BG encode principal bundles. They encode them precisely in this via this cocycle description, so these are called cocycles, these transition functions, because they obey the cocycle condition. Okay, so this gives you a principal bundle. What about equivalencies of principal bundles? So that is given from so-called coboundaries, which are maps from the patches into G. And it turns out that two principal bundles, I mean, this is a well-known theorem in ordinary bundle theory, that if I have two sets of transition functions related in this way, via such functions, then the bundles obtained from GAB and GAB tilde are equivalent. So they're essentially the same, right? This is just some kind of gauge transformation in my bundle, right? And how do you see this from the category theory perspective? Well, I didn't talk about morphisms between functors, but you can formulate such a notion of a morphism between two functors. This is called a natural transformation. And these natural transformations, again, they have some properties that they have to satisfy, so that all the structure of the categories and of the functors is preserved. And when you work out the definitions of the definition of a natural isomorphism applied to this case, so if you consider two such functors from the check groupoid into BG, one given by G and one given by G tilde, it turns out that the natural transformations precisely give you these coboundaries and this coboundary relationship. Right? So indeed, we can, everything about principal bundles can be understood just from this, let's say, abstract categorical perspective, which is good because now we can generalize it. We can generalize it to higher things. Okay. Unfortunately, categories will not be enough for that. We'll have to talk about higher categories. But let's first try to motivate why that is the case, why it's not enough. So when we try to do parallel transport of extended objects, so that means we replace paths by potentially higher dimensional surfaces. For example, we can consider the parallel transport of one-dimensional strings along a two-dimensional surface. I'll consider this particular configuration. So I have, this is string in configuration number 1. This is string, my string in configuration number 2, and this is my string in configuration number 3. And I move this string first to this configuration and then to this configuration, right? If I associated to each of these steps a group element, so in particular, as I move this part to this, and I associate to this action some group element G1. Similarly, I do that for this part. I associate to it an element G1 prime, and similarly G2 and G2 prime. It turns out that if I want to do this consistently, the following identity has to hold. First of all, the composition. So there are 2 ways how I can get from configuration 1 to configuration 3 via configuration 2. First of all, I can first move the left part from 1 to 3 and then move the right part from 1 to 3, or I can move first the left and right part from configuration 1 to configuration 2, and then the same from configuration 2 to configuration 3. And these 2 ways of transporting the string have to agree, have to give me the same answer. Right? And this is precisely this identity. So first I transport, so let's see. So first I transport G1 and G1 prime. So I do this into this configuration. And then from there, I move my string into this configuration by G2 times G2 prime. And that has to be the same as if I first moved, let's say, the right part. So G1 prime times G2 prime. So moving this part into this configuration, and then moving this part into this configuration, which is given by G1 times G2 times G1. And these 2 have to be the same. But this means if you set G2 equals 1 and G1 prime equal to 1, you obtain this condition. What does it mean? Because the G's were arbitrary, this forces your group to be abelian. This is the famous Ekman-Hilton argument. So you cannot do this prescription with non-abelian groups. So it seems like ordinary gauge theory fails to capture the parallel transport of higher dimensional objects. And this is a problem. So how do you solve this?
Oh, wait, sorry. Can you give me a second to digest this? So what do you mean by setting G2 equals to 1? Meaning
Well, I have this, so I obtained this identity. So this is the consistency condition. And now now you just set G in this condition, this has to hold for all group elements. So just set G equal to 1 and G2 equal to 1 and G1 prime equal to 1, and
Yes,
you obtain this condition.
yeah, I'm just trying to visualize what G2 equals 1 means, that I
Yeah.
don't transform it anywhere, I stay where I am.
Yeah, exactly. Yeah,
Uh-huh,
it
uh-huh.
means that you have the trivial, you don't do anything to that part. Yeah.
I see. Okay, so if I
Yeah,
set
so
it up to 1,
this can be imagined visually, right? So you just, it means
Yeah.
that you don't move. This
Yeah.
is the identity, and this is the identity,
uh-huh.
right?
Yeah.
And the two ways of transporting it have to agree.
Yeah.
Yeah, so you can actually see it from the picture that it has to commute. The group elements have to
Of
commute.
course. Yeah.
Yeah, so
Yeah.
that's a problem.
Okay, good.
So let's see how that problem can be solved. And it can be solved by going higher. So instead of categories, you use two categories. So let's first recall what we mean by a two category. We'll only be concerning ourselves with a strict two categories, fortunately, because otherwise it gets really messy really soon. So a two category or a strict two category, it just means that I take my category, right? So I had a collection of objects and collection of morphisms, and I take the collection of morphisms to be a category itself, right? So that means if this is supposed to be a category, I introduce some kind of higher morphisms or two morphisms into the game. And I introduce also a new map, a new composition into the game called the horizontal composition between two morphisms. So I'll just show you a picture, which will be basically the same picture that I drew previously. So this is an example of how you can visualize this. So the points are my objects in the two category. The arrows are my morphisms, or one morphisms, as I now call them, in this two category. And then I also introduce arrows between arrows, so morphisms between morphisms, depicted by these double-lined arrows, which give me the two morphisms. And now I have a way, so of course, because the C1 is supposed to be a category, so I have a way of composing two morphisms vertically, right? So I can compose eta1 with eta2. But now I also have another composition called the horizontal composition, which gives me a way how to compose eta1 with eta1 prime, or eta2 with eta2 prime. And when you work out, again, when you work out all the definitions, all the consistency requirements of this two category, you'll see that one of these requirements is the so-called interchange law. In other words, the composition is basically what I did previously in the previous picture. The fact that composition of these two, so if I first compose these two vertically and these two vertically, and then I compose the result horizontally, the result has to agree. If I first compose these two horizontally and then vertically compose the result of the horizontal composition of eta2 and eta2 prime. So that's the right side of the equality. So this is called the interchange law, and this is precisely what relaxes my the Ekman-Hilton argument, because now you see I have two distinct compositions in this case, and each one of these arrows contains information about its source and target. So it turns out that indeed now you cannot apply the Ekman-Hilton argument, because recall in that Ekman-Hilton argument, what you assumed was that this product and this product were the same, right?
Yeah, so you defined another characteristic of your transformation.
Exactly. Yes.
Okay.
So, yeah. But now, okay. So now it gets more complicated, right? Because you are working with two categories. So we have, first of all, you have more information. You have the objects, you have the morphisms and the two morphisms. But in order to talk about morphisms between two categories, you have to talk about two functors. So higher versions of functors. And again, just as with the two category, I was only defining for you the strictest possible version of a two category. I'll explain what I mean by strict in a bit. Again, you can have various versions of two functors. And unfortunately, the strictest possible version of a two functor will not suffice for our purposes. And we'll have to go, but I'll not give you any of the messy diagrams.
We might, if we do the exercise that we did previously. Who did we send to one? Was it, if you go back, maybe was it the previous slide or a couple of slides?
Yeah. So, I mean, if you imagine setting one of these to the identity.
Yeah.
I set this to the identity and this to the identity. So that means that this one and this one. And you see, you'll have the condition eta 1, the horizontal times, eta 2 prime has to be the same as eta 2 prime, the vertical composition, eta 1, right? So these are two different operations. So they can agree. So that it doesn't force your group to be abelian.
Good, thank you.
Right? Okay, so now regarding the strict and the various versions of categories and functors, well, two categories and two functors. So how do you construct higher versions of structures? Well, I mean, what is a mathematical structure? So that's a mathematical structure is given, you can understand it as being given by, well, so we have a set, we have some structure functions and some structuring equations. Categorification just basically heuristically means adding morphisms between morphisms. So you lift certain properties. First of all, your sets become categories because I add the arrows. Structure functions become structure functors. And structure equations become structure isomorphisms. So certain conditions don't have to hold on the nose as equations, but they can hold only up to some kind of isomorphism. So I add an arrow which will relate one side of what was previously an equation to the other side of that equation. So this is how I mean, this is a very heuristic description of categorification. And this process is not unique. It gives you variants. So for example, when you categorify group into a two group, first of all, I move from my set G into a category. The product and identity and the inverse, they become functors. So these were all some kind of maps on my group previously, but for the two group, those will be functors. And the group had to obey the associativity condition, right, which was an equation. But now in the two group case, instead this equation becomes well, it is encoded in an isomorphism, which is called the associator. So this kind of composition is related to this kind of composition. It doesn't hold precisely on the nose, but there is an arrow which relates the two. Okay. Yes. So.
Oh, sorry. This arrow doesn't mean equality. It just means somehow you can transform this one.
Yeah,
here.
exactly. Yes. No, that's precisely it. Yes.
Okay.
Okay. And similarly, the unit. So I had a unit in my category. Now I have a functor. Now I have a unitor. So that's some kind of transformation which transforms this object into this one. And right. And so in general, I distinguish the left and right unitors, whereas in the group they were the same, right? And similarly for the inverse, I have some kind of weak inverse, a notion of a weak inverse. So again, some kind of transformation which takes an x and associates to it its weak inverse such that I can transform it to 1. Okay. Don't worry about this too much because we won't need that. I'm just giving this as an example of how we perform the categorification. Because as I said, we'll only, for the groups and 2 groups, we'll only need the strictest possible version. But similarly, you can lift the definition of a functor into a 2-functor, relaxing certain conditions to hold only up to these kinds of isomorphisms. And what okay.
Sorry. Yeah. So this weak inverse, this is as opposed to
a strict inverse.
Oh, which does what?
Which does precisely, I mean, that would give you an equality, right? So
okay. Yeah.
So that will be equality on the nose here. Or for example, yeah, the associator, when the associator is trivial, when this map is the identity, this thing would be equal to this thing.
Got it. Yeah, thank you.
Okay, so you see that 2 group contains somehow more information, of course, than an ordinary group. But the point is that there are various versions, there's various variants of 2 groups. So this, what I gave you here, is the weakest possible one. If I take the associator to be trivial, the unitor to be trivial, and also the inverse to be trivial, that means everything holds on the nose as an equation, I get the strict version. I get the strictest possible 2 group. And fortunately, strict 2 groups, or strictly 2 groups, are equivalent to so-called crossed modules of Lie groups. What are those? So these are just given as pairs of Lie groups, G and H. Then we have an automorphism action of G on H. Furthermore, we have the morphism of Lie groups from H to G, such that certain identities have to be satisfied.
That's wonderful. The whole time I was thinking, this really sounds like the stuff we do in particle physics, and there you go, Lie groups. That's beautiful.
Yeah, absolutely. I mean, the reason we are using strict 2 groups here is that we want to really be able to provide the cocycle description of the connection, of the connective structure. Yeah. Which I mean, we really need to be able to differentiate, right? To consider Lie algebras of something. And yeah, for that we need, so first of all, for that we need Lie groups, and we are fortunate that we only need the strictest possible version. I mean, integrating weak Lie to algebras is difficult. It's not possible in general. I mean, it's possible, but it's not practical. Let me put it that way. Yeah.
Yeah. But this is beautiful. I'm having a lot of fun. Thank you. This is a really nice talk.
I'm glad. Thank you.
Sure.
Okay, so a crossed module of Lie groups is just pair of Lie groups with a morphism from H to G, together with an automorphism action of G on H, such that, first of all, this condition is satisfied. So when I act by G on H1, and I map it by T to my group G, then this just becomes the S-joint action. Okay, and similarly, I have this identity. This is called the Pfeiffer identity, which says that if I first map my H into G, and then I act on it with an H2, then this is the action by conjugation in my group H. All right, don't worry about it too much. I mean, we won't be needing that in practice, but all I wanted to say is the point of this is that you don't have to work with these messy categorical diagrams. You can be very concrete in the strict case. So strict two groups really are just crossed modules of groups. Okay, and that's important because they will play the role of structure two groups for principal two bundles. So yeah, that's what I mean by gerbes. Okay.
Oh, so you finally used the word gerbe. I've been waiting for this.
Yes. So gerbes for me are principal two bundles with a. So for the purposes of this talk, gerbes are principal two bundles with strict two groups as structure two groups.
So this gerbe actually has something to do with the French gerbe, which means a bundle, basically.
Yes, exactly.
I see. Okay.
Yeah, so these are like higher bundles. Yeah. Okay, some examples are needed. First of all, the B1 case, right? So we recall the BG that was just G double arrow single object, right? So that was the group G viewed as a one object groupoid, and by the way, how much time do I have? Because I mean, I'm kind of going very, very slow over the notes, but
there's no limit. We go until you have energy.
Oh, there's no limit. Okay.
We are relatively relaxed about time.
Okay, great. Well, then feel free to interrupt me as much as possible. Okay. So B1 underlies an abelian gerbe. That is an example of a strict two group, because it can be shown that this has an underlying crossed module of Lie groups, which is just this one. So I take G to be the trivial group, the group containing only one, and U1 is my H, right? The map T is trivial. I just map the whole group to the identity, and the action is also trivial because I just act by the identity on the group U1. So this is precisely equivalent. I'm not going to be showing it here, but it's not difficult, to B1. And this
but
is
this
what
doesn't have to be a strict one. I mean, even if it was weak, the abelian group would still hold all of this.
Yes. But in terms of, I mean, abelian gerbes are precisely given just by this data. So if you have, I mean, it is strict by. It turns out to be strict, right? Or did you have something else in mind?
I was just thinking, well, I mean, in the sense that you were defining strict and weak, I guess, yeah, it doesn't have to be strict. It could also be weak, and it will hold all the.
Sure. It just, all I'm trying to say is that this correspondence between crossed modules of groups and strict groups, crossed modules and two groups, that's only given for the strict case, right? Because the weak contains more. The weak
Yeah.
contains also the associator, the uniter, the Wig inverse, and so on. It contains more information.
Yeah.
But in the strict case, there's one-to-one correspondence.
Yeah.
Okay, and the abelian gerbe is precisely encoded by such a strict Lie two group. So this is the structure two group for an abelian gerbe. Okay, so that's one thing. The other example of a cross module is this one. So I take my group H to be just the identity and my group G to be just some Lie group G. Then the map T is just the trivial inclusion of 1 into G. And then I also have the trivial action by automorphisms, which is just the identity. Okay, this underlies a principal G bundle. Don't worry about this comment now. But this is how you can encode an ordinary principal G bundle into this higher picture. I'll explain what I mean by that in a second. Another example of a strict two group is this space LG. Okay, so remember this notation because I'll be using that. So LG is just given as a pair of these two groups. So P0G, which is the space of based paths in G, and my group H is just the space of based loops in G. So if I have my space G, here I have my identity, I consider all the paths in G, this gives you the space of based paths in G, so P0G. Similarly, you can construct the loops, which begin and end at 1 in G, and this gives you the space of based loops in G. Okay, I have the adjoint action, so the action by conjugation. That's this triangle, and the map T is just the ordinary inclusion because I know that every loop is also a special kind of path, right? So that's an ordinary inclusion, and this gives me. I mean, you can again check all these identities. It turns out that they hold. So this indeed gives you an example of a crossed module of Lie groups. And as you can see, this crossed module only contains, I mean, the information here is only coming from G itself, right? So I only provide group G and I can construct such a cross module. So it seems like this should be somehow equivalent to this one. I mean, they both contain the same information. So the question is, are these two equivalent? First of all, we have to specify what we mean by equivalence of crossed modules. Again, you can start from the categorical definition, so you can formulate the equivalence between strict two groups. And it turns out when you do the exercise and so on, it turns out that the diagrams which give you the equivalence of two crossed modules. So here's one cross module, here's another cross module. And an equivalence is given by this particular diagram, which is called a butterfly, a flippable butterfly, in the case that it is an equivalence. So what does it mean? I have one cross module, second cross module. A flippable butterfly is given, I'm given also a Lie group E. So this is another Lie group. And morphisms like this, such that this diagonal and this diagonal, they have to be short exact sequences. So when these two diagonals are short exact sequences, and when the whole diagram is commutative, then you can say that these two cross modules of Lie groups are equivalent. Okay. So let's see if these two are indeed equivalent. And it turns out they are. I am able to find such a group here in the middle, so that these two diagonals are indeed short exact sequences. By the way, there are two more extra conditions which I'm hiding under the rug. But yeah, they can be easily checked that they hold. Yeah, there's something more to check for the flippable butterflies here, but I'm not just really too. It's not important at the moment, but just as a caveat. Okay, so let's see. Is this a short exact sequence? Well, this is just the inclusion, and this is just the endpoint evaluation. So what is that? I take my path in G, starts at 1, ends at some point G, right? And the endpoint evaluation, all it does, let's call this G with a circle, it associates to this path its endpoint. So this point G, right? So that's my map B flat, using the musical notation. And indeed, that means that this is indeed a short exact sequence. And this is also trivially a short exact sequence because I'm just including the 1 here and taking the identity map here. So indeed, these two cross modules are equivalent. Okay.
What are the two extra conditions that you're sweeping under the rug?
Right, so that is something to do with preserving these two conditions.
Uh-huh.
So there's some kind of extra equality identities that have to hold. Okay. So they are indeed equivalent. So they indeed encode the same amount of information. Okay, so let's now see how one can formulate these higher bundles using the ingredients that we already have. Well, sort of. So principal G bundles, where this G is the curly G, right? So that's a crossed module of Lie groups. That, I mean, just repeating the exercise from before, from the ordinary case of ordinary principal bundles, that will be a two-functor, some kind of two-functor, from the check two-groupoid into the space B of G. So I'm now gonna explain all the ingredients that are there. So I start with a crossed module, and I said that this is a strict two-group. Strict two groups, just as ordinary groups, where special kinds of where one object groupoids, two groups can be embedded into two groupoids. I do it as described here. So it turns out that the two group associate, so this is associated to some two group, let me call it G with a hat. And I can embed that into a two groupoid with a single object. So here's my single object. And it turns out that so that these two are equivalent, you need to take the one morphisms to be G and the two morphisms to be the semi-direct product of G and H. It is just what is required so that all the conditions are satisfied. So this form that's uniquely fixed. Okay, so that's my space BG. So it's a two category of this form. Okay, and the check groupoid or check two groupoid, it turns out that I only need to trivially extend my check groupoid, which is this part of the picture, into a 2 groupoid just by adding the identity 2 morphisms. So this is literally just embedding the ordinary check groupoid into 2 categories. Because all I did was I added the identity 2 morphisms. And yeah, I use this notation for that. But as you can see, there is nothing more. Nothing more is needed. You don't have any triple overlaps or anything more complicated than was already contained here. This is just a way how to embed ordinary check groupoids into 2 categories. So now you have these two. Now you have these two groupoids, the BG associated to the Lie crossed module G, and the check 2 groupoid. And now all the important or all the meat is contained in this 2 functor. I didn't give you a definition of a 2 functor because that is quite messy, because I said that we don't actually, it's not enough to consider the strictest possible version of 2 functors, and you have to really work with something that is called some kind of weak 2 functor. So that contains a lot of information and a lot of diagrams are involved, but when you formulate, I mean, the exact details can be found in our paper and in the references within that. But it turns out that when you unpack the definition of the 2 functor, you apply it to this case, it turns out, I mean, after doing the exercise, that you obtain the following data. So first of all, from this, you are given the transition functions GAB valued on double overlaps and HAB. So GAB, that's a map. GAB is a map from the double overlaps into G. And we also have HABC, which is a map from triple overlaps into H. Even though the triple overlaps are not anywhere to be found here, they are indeed contained, the information about them is indeed contained in this 2 functor. So I'm not spelling out all the details here because that would be quite complicated. But if you are interested, I invite you to read the paper and, well, the references in the paper. I mean, all these details can be found there. Okay, so, and we have these transition functions, and they have to obey the following cocycle conditions. So first of all, we have this one, which, as you can see, if I hide this term, if I delete this term, then this is the cocycle condition I had for ordinary principal bundles, right? So I can see that now what was the ordinary cocycle condition for principal bundles is now relaxed. It has to hold only up to this term. So T of HABC, where T is this map. Okay, and furthermore, the H's, they also have to satisfy certain cocycle condition. I'm just giving it here as so that you see that something like this exists, but we'll not be needing it, fortunately. But yes, there is some kind of cocycle condition. As you can see, A, B, C, and D are involved. So that means that this needs to hold on quadruple overlaps, right? So, and when you are given this data together with these conditions, this encodes for you a principal 2 bundle where the 2 group is is given by the crossed module of Lie groups. So this is what I'll mean by a non-abelian gerbe without a connection. There's no connection yet. We'll get to that. But this is just the topological description of non-abelian gerbes. Okay. Now equivalencies. So when are two such principal two bundles equivalent? Well, that happens again doing this exercise with morphisms between two functors. So you obtain some kind of let's call them pseudo-natural transformations. Doing this exercise will provide you the following data. They'll give you boundaries, so those will be maps from the patches into group G and from double overlaps into group H, such that the following equations have to hold. Right, so again, this is some new equation. We don't have to study that in too much detail, but I just want to point out to you that this is precisely, if I delete this H term, I obtain precisely what I had in the ordinary principal bundle case. So indeed, this is precisely how you should think of what categorification does to you, or does for you. You relax what was previously an equation, that these two were related by an equal sign, to hold only up to some new bit, some new term. So this is precisely what encodes for you the transformation between this side and this side. Okay. Right, so this is the topological description of gerbes without connections. And now we want to get connections into the picture. So how do we do that? Well, I mean, in ordinary principal bundle case, we had a group G, and what were connections? I mean, locally, connections were just one forms valued in the Lie algebra of G, right? So in order to be able to describe connections, at least locally, we need to be able to talk about some kinds of Lie algebras for these two groups. So let's look at that. So it turns out that we can easily differentiate a crossed module of Lie groups just by applying the so-called Lie functor to the two group. And what that yields for you is a crossed module of Lie algebras. So that, again, is given by a pair of Lie algebras, where G is just the Lie algebra of my group G, and H is just the Lie algebra of my group H. And all of the maps that were involved in the crossed module, that were part of the definition, part of the package of the crossed module of Lie groups, they are there as well. So I have the automorphism action of the Lie algebra G on H, and I have the morphism of Lie algebras from H to G, right? So again, if I wanted to use the same notation I did for the cross module of Lie groups, I'll just have G into H, T. Yeah. So it's slightly abusing the notation because these are the differentiated versions of the maps. They are not those maps per se. Okay, and then differentiating the identities that have to hold for cross module of Lie groups yields for you this identity. So this is just the linearized version of conjugation, right? Yields a commutator, and yeah, here you also had conjugation, so yields a commutator. Okay, so these are crossed modules of Lie algebras. They are just you should think of them as really so what Lie algebras were to Lie groups, cross modules of Lie algebras are to strict two groups. All right. there is another name for the crossed modules of Lie algebras. They can be viewed as strict two-term L-infinity algebras. So they provide for you an example of a very simple L-infinity algebra, namely strict. It has to be strict and two-term. So I'll describe L-infinity algebras in greater detail in a moment, but let's just start with this simple example of a strict two-term L-infinity algebra. So I have a Z-graded vector space that is only concentrated in degrees -1 and 0. The degree 0 elements are just the elements in G, and the degree -1 elements are just the degrees are just elements in H. I have the differential, which is given by T, and I also have some kind of graded antisymmetric Lie bracket on this space, which is encoded precisely in the commutator. So on G I have a commutator, also on H I have a commutator, and this action also encodes some kind of so this triangle is an action of G on H, and the commutator and the action can be neatly packaged into a graded antisymmetric Lie bracket on this space. Okay, and these conditions, they just translate to the fact that mu1 is a derivation. I mean, that's very simple to see because that's basically just yes, that's basically just this condition. And the mu2 have to satisfy a graded Jacobi identity, which is just the fact, which is just ordinary Jacobi identity for the Lie bracket. So indeed, this gives you an example of an L-infinity algebra. Okay. For well, the equivalences, as I said, were given by flippable butterflies. If you differentiate that diagram, you would get a notion of equivalence for crossed modules of Lie algebras. And this notion turns out to be the same as the notion of equivalence for L-infinity algebras, which is the notion of so-called quasi-isomorphism. The word quasi just means that you have an isomorphism on cohomology of this complex. So you have this complex of algebras, and looking at the cohomology of this complex gives you a certain model for the L-infinity algebra, and isomorphisms of cohomologies give you a notion of a quasi-isomorphism or equivalence of L-infinity algebras. To picture this, you can imagine precisely in the strict two-term case, you can just imagine these flippable butterflies in the, I mean, when you linearize, when you differentiate that diagram, you obtain the same diagram. I mean, just with Lie algebras, and that's what is meant in this particular case by a quasi-isomorphism. Yeah, so equivalences of L-infinity algebras. Okay, so when you differentiate this space LG, so recall that LG was just my space L0G into P0G with the adjoint action, with the action by conjugation. If I differentiate this, what I obtain is a crossed module of Lie algebras, where the G becomes the Lie algebra, and I obtain so P0G is the space of based paths in my Lie algebra G, and L0G is the space of based loops. And this together is an example of a crossed module of Lie algebras. Okay, so I'll be needing all of this in what's coming. Okay, but let me first insert a couple of comments on L-infinity algebras. So L-infinity algebras, they are just generalizations of differential graded Lie algebras. So I have the graded structure, I have the Lie algebra structure, and I have the differential structure. So I have a derivation. And I generalize this, and I obtain in a particular way, and I obtain the notion of an L-infinity algebra. So first of all, is a graded vector space with totally antisymmetric multilinear products, mu I, which again have some degree, and they satisfy certain identities. First of all, the map mu1 is a derivation, so we have a complex. So mu1 squares to 0. So if I write it as L minus 2, L minus 1, L0, and so on, I have this mu1. And the statement is that mu1 composed with mu1 is 0, right? So that's the first identity. That just means we are dealing with the differential complex. The second identity is that this is indeed some kind of derivation. So mu1, so I have the bracket mu2, which gives me on L0, that gives me the Lie bracket, right? So on my space L0, mu2 maps us from L0 times L0 to L0, and it is antisymmetric and satisfies some kind of Jacobi identity. So this is some kind of Lie bracket. Okay, and all of these maps, mu1, mu2, mu3, and so on, they have to be compatible in a particular way. One of these identities is written here. This is just the graded derivation property of mu1 with respect to mu2. Then there is a higher version of a Jacobi identity, the fact that mu2 of x1, mu2 x2, x3, plus cyclic permutations of that, plus or minus cyclic, that depends on it's graded now, so you have to be really careful about the signs. Well, okay, anyway, that has to be equal to mu3 of x1, x2, x3, plus or minus cyclic combinations. Okay, so this, the map mu3 lifts the Jacobi identity in the precise, precisely in the sense of categorification that relaxes the Jacobi identity to hold only up to an extra datum given by this map mu3. Right, so this is an L-infinity algebra. They are nice. L-infinity algebras are nice because they come with their own gauge theory, so-called homotopy Maurer-Cartan theory. So let me describe that. First of all, elements of degree 1 are called generalized gauge potentials. Elements of degree 2, which have this form, that is what I call the curvature. Okay, so we will digest that in a little bit. Just for now, I have these abstract equations. And the homotopy Maurer-Cartan equation then just means f equals 0. So this is the vanishing of the curvature. The curvature f obeys a generalized Bianchi identity. Again, it has this form. And right, okay. And elements of degree 0, they give you gauge transformations. Again, generalized gauge transformations. So let us see how this. Okay. Before we move to concrete examples, let me just add a couple more comments. So equivalences between L-infinity algebras, as I mentioned, they are given by quasi-isomorphisms. So we saw an example of the quasi-isomorphism in the two-term case. So when the only non-vanishing when your L-infinity algebra is concentrated only in degrees -1 and L0, this was the two-term case. This is a two-term L-infinity algebra. And the strict case means that mu I is 0 for I greater or equal than 3. So the only non-zero higher products are mu1 and mu2. So when you have an object like this, so space is L-1, L0, with these maps such that they obey certain conditions coming from these homotopy Jacobi identities, you are dealing with a strict two-term L-infinity algebra, which, as we saw, is just a crossed module of Lie algebras, and equivalences between crossed modules of Lie algebras are given by flippable butterflies. So these were examples of quasi-isomorphisms. Right. If my L-infinity algebra is equipped with a metric, we can write down an action which reproduces for you this equation, the homotopy Maurer-Cartan equation. So you obtain a homotopy Maurer-Cartan theory, which is a higher gauge theory modeled on the L-infinity algebra. This is nice because there is a statement that any field theory is a homotopy Maurer-Cartan theory for some L-infinity algebra. So you can basically package all your operators appearing in the field theory, such as the kinetic operator and the interactions, into an L-infinity algebra, into these maps, mu2 and mu3, mu4, and so on. All of that can be packaged into some kind of L-infinity algebra, such that when you give me a homotopy Maurer-Cartan action, this is actually equivalent to my original field theory.
Is this statement proven, or is it a conjecture?
This is proven on tree level. And for loops, I think it's also true. But I don't know the details of that. But I think it's also true for the loop level. So, but I think at tree level it's pretty straightforward. But at loop level, one has to work harder.
Thank you.
Okay, now, and the thing is that ordinary gauge theory.
Just to follow up on that, what about for non-perturbative stuff?
Yes, so that would be given by loops, right? Sorry, non-perturbative. Okay. That I'm not sure about, but yeah, I'm not sure about the non-perturbative picture. Yeah, I cannot make any other comment than this. So at the perturbative level with loops, it should hold, but I'm not sure about the non-perturbative.
Okay, great, thank you.
Okay, so ordinary gauge theory on a manifold M is modeled on what? So, as I said, ordinary gauge theory deals with connections and curvatures. So the connections are one forms. So it's a one form. It lives in omega 1 on my space-time, valued in some Lie algebra, and the curvature is a two form, valued again in this Lie algebra. So this is for ordinary gauge theory. So I can say that what I need to do in ordinary gauge theory, I need to construct this tensor product of the de Rham complex with my Lie algebra. If I want to do the same thing for higher gauge theory, sorry, I'll just have a sip of water. If I want to do the same thing for higher gauge theory, I need to be able to construct this tensor product of an L-infinity algebra with my with the de Rham complex. It turns out that this space is again an L-infinity algebra. Okay, so how do I perform this tensor product? This is, by the way, what will play the role of connection data, at least locally, on a principal 2 bundle. So first of all, I said that gauge potentials live in degree 1, right, in this space. So to perform the tensor product, you need to add the degrees together. This is a graded space, this is a graded space. So you just multiply each subspaces together so that they add up to the right degree. So first of all, you start with a, okay, so first of all, we'll be only needing L-infinity algebras which are concentrated in non-positive degrees. So my L will be L0 plus L minus 1 plus L minus 2 plus, and so on, up to how many terms I need. In our case, we'll only need 2 terms, fortunately, because then it would be much more complicated. So if I perform this exercise, so so omega dot is just omega 0 plus omega 1 plus omega 2 and so on, all the way up to the dimension of my spacetime. And I multiply those things together, so the degree needs to add up. So this is 1 plus 0 is 1, 2 plus minus 1 is 1, and so on. This gives you a degree 1 element in L hat in this tensor product. Right? This is how you get the connection forms. So the connection will be parametrized by a 1 form living in L0, a 2 form living in L minus 1, a 3 form living in L minus 2, and so on. The higher products are obtained very, very easily. So mu2 just becomes the composition of, sorry, there should be heads here above mu2 and mu3. So mu2 head is just, let me just very briefly sketch. This is mu2 composed with a wedge of tensor products, right? And mu3 is then just mu3 and so on. The only contribution comes into mu1 head, and that is here you combine the D. So I have the de Rham differential on this complex, and I combine that with mu1, and that's what gives me the mu1 map on this space. Right, so this describes for you this L-infinity algebra L hat. So first of all, degree 1 elements are the connection forms. I have the higher products. And now, if you work out the curvatures from this formula, so you have this formula for the homotopy Maurer-Cartan theory. When you work out this, in this particular case of L hat, your curvatures are now parametrized as follows. You have the 2 form curvature valued in L0, right? 2 plus 0 is 0, and the curvatures have to live in total degree 2. I have the 3-form curvature, which is a 3-form valued in L-1, so the total degree is 3 minus 1 is 2, so that's correct. And all of these have the right degree, so you can combine them together and actually obtain separate identities out of this one identity. So we just had one identity here, right? But for degree reasons, they combine into separate ones because they live in different spaces. And you obtain a formula for the curvatures. So F and H, and potentially higher terms as well. But for us, only F and H will be sufficient. So by the way, as you can see, this seems like the ordinary curvature in ordinary gauge theory, right? Recall that in ordinary gauge theory, the formula is this. So dA plus 1/2 the commutator AA. But I said that mu2 is basically the commutator, right? So this is the ordinary curvature. And in higher gauge theory, you have an extra term here. You have this contribution from the connection 2 form. And this combination of terms I call fake curvature. Don't ask me why. It's just the way it was called in literature. And I also have a formula for the 3-form curvature. And as you can see, if you remember from the beginning of my talk, I had the self-duality equation. I had H equals dB equals Hodge H, right? So this was just this first term, but now I have the contribution from the A as well. So this truly has the potential to describe interacting non-abelian theories, because I have this. I have these extra terms here with A, so interaction between A and B and so on, and A and A and A. Okay. So this is how I obtain the curvature formulas. Again, doing this exercise for degree 0 elements gives you gauge transformations. And it turns out that these formulas uniquely fix for you the gauge transformations. That is because infinitesimal gauge transformations can be understood as partially flat homotopies. That just means that so let's say you have the curvatures, I said this is a 2-form living on space M valued in G. This is a 3-form on space M valued in H, where G is, L0 and H is L-1. And it turns out that if you extend your space, your manifold, by an interval, and you consider a homotopy between two theories. So you again consider the same setup as before, the same formulas, but on a larger space, M times the interval. This is how you describe the homotopies. It turns out that if you require partial flatness, so flatness along the t direction, and h dx equals 0, this recovers for you the gauge transformations. So in particular, let me see, do I have these formulas here? No, okay, let me just write it down. In particular, you know how A will transform. A will transform as d alpha plus mu A alpha minus mu1 of lambda. So first of all, gauge transformations are parametrized by functions living in L0 and one forms living in L-1. If you've heard about this program of generalized symmetries or categorical symmetries, this is by the way how they start usually, how they motivate the program. The fact that you have higher form symmetries in your theory, right? for example, H equals dB, this equation is invariant under the shift B goes to B plus d lambda, where this is a one form. So I have a one form symmetry in B, and I can easily recover that here. I can easily see that here. So my gauge transformations are parameterized by zero forms valued in L0 and one forms valued in L-1. And these formulas, by this partially flat homotopy prescription, fix for you the gauge transformations. Sorry, minus mu1 of lambda. So this can be obtained from this formula. Okay, that's all I wanted to say on this point.
Oh, I have a question.
Yeah.
So you said you could then basically write your gauge transformations in this formalism.
Yes.
Do you mean that this actually has an application, and I can, I have a model with certain gauge transformation, I can, embed it in here. Does it have all the information of the set model?
Well, I mean, if you give me, if you give me this data, this and these formulas, everything is set, everything is fixed. I mean, you can obtain the gauge transformations, and the gauge transformations give you the consistency requirements for your theory. So that you see, these formulas have some kind of symmetry. I mean, the B has a one form symmetry, the A has a zero form symmetry, and so on.
I see. Okay.
So yes, I mean, this doesn't give you the theory itself, right?
Yeah.
It gives you the ingredients of the theory. But this is the framework. This is the right framework how to that you should use to formulate your actual theory, then your actual model afterwards.
Yeah.
Just as it turned out that for ordinary gauge theories, the right framework was principal bundles with connections, right? I mean, it took some work to realize that this is the right prescription for the curvature, right? And similarly, you do the same exercise, similar exercise here. Okay.
And in the beginning, you said that you don't necessarily need to have the Lagrangian to be able to do all of this analysis.
Yeah, absolutely. I mean, you don't have any particular Lagrangian in mind here. I mean, there is, of course, there is the homotopy Maurer-Cartan action associated to this L-infinity algebra, but that basically just gives you the form of the curvatures. So that's basically a mathematical trick how to obtain this, how to obtain a consistent high gauge theory, right?
Yeah.
But what I said just now is bollocks, because it's not consistent. It turns out that consistency requires part of your curvature to vanish. That is a problem, because when this is zero, it turns out that you can gauge away any interacting part in your theory, and your theory becomes abelian. That means that the H will turn out, I mean, you will be able to gauge away all the other terms here, all these terms here, and you basically can just work with H equals dB, the abelian theory, or the interacting theory, the non-interacting theory, that all follows just from this, just from the fact that F equals 0. I mean, it's similar to the ordinary principal bundle case. There, if you have this formula, and if this is 0, it turns out that A is pure gauge, right?
Yeah.
So you don't have any information.
Yeah, I see.
In A. And that is true, almost true here. The only information you have here is precisely in the abelian part of B. That's the only information that is left after imposing the fake flatness condition. And you need to impose the fake flatness condition because otherwise your theory is inconsistent. In particular, that means that infinitesimal gauge transformations, they do not close. You want this to hold, but you have an extra term bit. I mean, you can get away around this problem if you kill this term. If mu3 is 0, then this term is not there. But if you then try to formulate the finite gauge transformations, the finite gauge transformations do not compose, even in this case, unless this is imposed. So this is really a big problem, and this was part of the reason why people abandoned like non-abelian gerbes for a while, because they just thought that this is lost cause. They could not overcome this problem. But there is a way how to overcome this problem. And the solution to that is to introduce an extra datum on your L infinity, on your crossed module, which is called the adjustment datum. So if I work with the crossed module of Lie algebras, right, H to G, and have the action, then it turns out that I need some extra bit here, some extra structure here, some extra map, kappa, which is a map from G times G into H. And once I have this map, I can hope to overcome. Sorry, no, I can hope, but I mean, I'll fulfill this hope in this talk. The important bit is that you require really this extra bit. Then, when you have this map, you can modify your curvature H. Basically, H will be what it was before, plus kappa AF. So A is my 1 connection, and F is my 2 curvature. So I add this term to H, and then it turns out that this is no longer required. By the way, you might wonder how just adding this extra structure lifts this condition, how it kills that condition. It's true. I did not mention this kappa has to obey certain identities, which I'm gonna list in a while. I'm gonna show them explicitly to you. So there are indeed some extra conditions on the kappa map, so that indeed this condition is lifted. But if you give me this kappa, which satisfies the conditions, which I'm going to show you, then you can perform this transformation of H, well, redefinition of this H. And it really is redefinition. There is a way how to mathematically motivate this. I don't really have time to provide all the details, to provide the details here. You can find them in the paper, but it's quite technical. It basically has to do with going back to the basics and showing why you thought that already these formulas were the right idea. Revisiting the fundamentals of this leads you to something what is called way algebras. And so the gauge theory can be encoded in an object, in morphisms from an object called the way algebra of an L infinity algebra. Morphisms from this space into my de Rham complex. And this basically gives you precisely these formulas. That's an equivalent way how to encode, how to obtain these formulas. And there, it turns out that there is a choice. It is possible to perform a field redefinition in this way algebra of my L infinity algebra precisely of this kind, which shifts the H by this one and still fulfills all the other requirements that you had for that previously. So all I wanted to say by this was that there is a mathematically well-motivated way why to perform this redefinition of your curvature H. It doesn't spoil basically anything, it just improves the theory. And it improves it in such a way that it lifts this fake flatness condition. So this is no longer required. Okay, let me just give you examples of the adjustment map. The first example is the space I considered already, the LG, right? So the based paths in my Lie algebra G and based loops. The gauge theory modeled on this L-infinity algebra will be given as follows. So my connection is a one form valued in P0G and also a two form valued in L0G, right? So one forms are paths and two forms are loops in my Lie algebra G. Then curvature forms are just applying, so just considering these identities I had previously and adding this extra term in there, working out the definitions in this particular case of L0G, of LG, I obtain these formulas, right? So these are my two form. So it's a two form valued in paths and three form valued in loops. And this kappa map in this particular case of LG is just the following map. So I take the commutator. So I take the commutator of A and F and I map it to a loop. So I construct a loop out of this. I'll explain all these maps. So first of all, we have the endpoint evaluation here. So because A and F, they are both paths, I can apply the endpoint evaluation to them. So it just gives you the endpoint of the path. And then you just construct a path out of this endpoint just by multiplying it by an arbitrary but fixed path. So that's a map from the interval into real numbers, such that at 0 it vanishes and at 1 is 1, right? So in this way, what I'm constructing in my space, so imagine this is my Lie algebra G, here is my 0, and what I do is I construct a straight line which ends at the commutator of AF, sorry, the boundary of that. So the commutator of A and F, both of these are paths. That gives you some other path in this space G. When you consider the endpoint, so you look just at the endpoint of this path, and what I do is I construct a straight line to this endpoint. So I have two paths. First of all, I have the path which is the commutator itself, and then I have this straight line here, which is given by this term. I subtract the two and I get a loop. That's all kappa does for you, because you need to be able to find a map which takes two paths and constructs a loop, right? That's what it does. And indeed, it fulfills all the hidden requirements on the map kappa. That's, by the way, the difficult part. I mean, solving those requirements, because I mean, it is easy to imagine a path, a map which takes two paths and constructs a loop. That's not so difficult, but constructing one which requires which fulfills all the other requirements, which I'll show later, that kappa needs to satisfy, that's slightly more difficult. But this one does it. So all I wanted to say by this is that if you give me a higher gauge theory modeled on this L-infinity algebra, in particular, I have the connection 1 form and 2 form, valued in paths and loops of a Lie algebra. I have these particular curvatures. Then I'm saying that this whole structure is consistent and gives you and is able to describe non-trivial interacting non-abelian high gauge theories. And that's all thanks to this term. Okay, slightly more involved example is the string Lie2 algebra. That's just the central extension of this case, right? You can see that I just centrally extend this part by R. That gives me an example of another strict two-term L-infinity algebra called the string Lie2 algebra. And again, for this case, I can formulate, I can find an adjustment datum. By the way, this is a very important example because that actually gives you non-trivial examples of non-abelian gerbes. Okay, and the map, the adjustment datum in this case is just obtained from the adjustment datum, which was in the case of LG, and some extra bit here. So what is this? I know that A and F are my paths, right? So they depend on some kind of parameter R. I can consider for example, Killing-Cartan form on G. So I take G with the Killing-Cartan form. So I consider the product of AR and FR. I differentiate one of them with respect to R, and I integrate the result from 0 to 1, and I obtain something which is valued in R. And it turns out that this is precisely the map that is needed to satisfy the conditions on kappa, the extra conditions, which I'll show you later. So this indeed is an example of an adjustment datum. Okay. Is there a question in the chat? Okay. Right. And let's now glue this all together. So we'll have a manifold, ordinary manifold, which we will cover again by some patches, UA. And now to construct such principal two bundles with connections, we'll combine all the ingredients together. So first of all, we have a Lie2 group and a 2 algebra, which are given by crossed modules of Lie groups and Lie algebras, together with this map, adjustment datum. So you can see that this adjustment datum is slightly different from what it was previously. Previously, I had this G times G into H, but it turns out that for the global picture, you need to half integrate this map. So you need something which is valued in, which takes an element in the group, and an element in a Lie algebra of this group, and maps it into something in the Lie algebra of H. So that's this map. By the way, it's called adjustment datum and denoted by the same letter because when you linearize it in G, right? When you differentiate the G in this map, you precisely obtain the map here, which is not surprising. Okay, but let me now describe the result. So here I have, here I have two columns, just to compare the ordinary principal bundle case to the higher case. So in ordinary case, I said that my principal G bundle topologically is described by these transition functions, which are valued in G. In the principal two bundle case, I have two sets of transition functions. First of all, GAB, which take me from double overlaps into G, and HABC, which take me from triple overlaps into H. Okay, these transition functions, they have to satisfy cocycle conditions. So in the principal G bundle case, it's just this condition. In the principal two bundle case, this condition is lifted to hold only up to this term, plus the H's have to themselves satisfy some kind of cocycle condition. The equivalences between such bundles are given by coboundaries, which have to satisfy the following identity. In the case of principal two bundles, we already saw that. This is nothing new, so it's these formulas. Okay, but now the really interesting stuff is now inserting the connections. So for principal G bundles, we had the connection 1 forms valued in Lie algebra of G and its associated curvature on each patch, right? Each patch, UA, I have locally, I have such a 1 form, which has to be glued appropriately on intersections, right? I'll show you these formulas in the next slide, how to glue this properly. Okay, in the case of principal two bundles, I have connection 1 form valued in G, and a connection 2 form valued in H, right? Both of these are on particular patches, and I also have the curvatures, which again, these are the same formulas are used in the previous slide, so nothing new here. And also I have the gauge transformations, right? The equivalencies between these connection forms. So in the case of principal G bundles, this is the formula. This is just the gauge transformation on a single patch between A and A tilde. So any two such configurations are considered physically equivalent. And in the case of principal two bundles, again, you have some formulas, but now, as you can see, you have a similar formula here, but that has to hold up to a 1 form, right? So now the gauge transformations, as I said previously, they are parametrized by elements G and lambda. G is a group element valued in, so that's a 0 form on patch A, valued in group G, and lambda is a 1 form, sorry, 1 form on patch A, valued in the Lie algebra of H, right? It's correct because this is valued in Lie algebra of H, so T maps it to G. Okay, so this is how this, by the way, obtained, as I said, from the definitions. These formulas are obtained from the definitions of curvatures.
And you don't call that fake curvature here?
Sorry?
You don't call that fake curvature here?
No, we call that fake curvature still.
Okay, yeah.
Yes, so indeed, this F that goes here, that's the fake curvature, not this one.
Yeah.
Okay, so this is the setup. This is how locally you describe the connections on a principal two bundle. And now gluing this together basically amounts to describing describing what happens on overlaps, right? So I mean, this is surjective submersion. I mean, that's not important. The important bit is that you have the cover, right? You have the cover of a manifold. Yeah, saying this more generally, you say that you have a surjective submersion, and you have an adjusted cross module. So you are given this data. Again, this is just repeating what was on the previous slide. And now gluing this together, the connections together, so on overlaps, your connection 1 and 2 forms have to obey the following relations. So first of all, we have the cocycles G and lambda in this case. Again, G is a 1 form, in this case, valued in, so it maps us from the overlaps into G, and lambda is a 1 form, which maps us, well, it's a 1 form on UAB and valued in H. Just as it was for gauge transformations, I just add an extra index, right? And as you can see, the formulas, these two formulas, they are the same as they were for gauge transformations, right? So the formulas here, they are completely the same as formulas here. It's just that this time I'm working over overlaps. So these cocycles, they have now 2 indices, right? This G and lambda. But what's distinct from the case of coboundaries or gauge transformations is the cocycle condition that the lambdas have to obey, so that all of it is consistent. So this is the condition that's required on triple overlaps. So on U, A, B, C, the lambda I, J, sorry, not J, AB, okay, lambda AB, lambda BC, and lambda AC, on triple overlaps, they have to be related in this particular way. This is uniquely determined by the fact that you want these conditions to be consistent. What does consistency in this case mean? It means that if I first transform AI to AJ, so let's say I'm working on triple overlaps IJK, and I first go from AI to AJ by this formula, then I go from AJ to AK again by this formula. The result has to be the same as going in one go from AI to AK, right? That gives you some kind of consistency condition on the lambdas. And that is all that is required. Everything, all that is, that is all that is required for A's. So once this and this holds, the cocycles for A and lambda are completely consistent over any number of overlaps. Now, doing the same exercise for B, showing consistency for the transformations of B. So if this term wasn't there, so you would be in the unadjusted case, so you don't have the adjustment. The consistency on B would turn out to be precisely the fake flatness condition, the fact that the F has to vanish. If this condition was satisfied in the unadjusted case, then the B transformations would be consistent. That means going from B to BJ, BI to BJ, and to BK is the same as going from BI to BK. Okay? But if this term is there, it turns out that as long as this map satisfies these two properties, you don't need the condition Fi equals 0. So this is no longer required as long as this map satisfies these conditions. And in the two examples that I showed you, the map that is provided indeed satisfies these conditions. So indeed, those two examples give you a consistent non-abelian higher gauge theory. And not just that, they give you more. They give you a non-abelian gerbe with a connection, right? So globally, you can describe these higher principal bundles in these particular cases. So anytime you give me a map, kappa, which obeys these conditions, I'm able to provide a non-abelian gerbe with a connection. And the two explicit examples I've shown you. There are more examples. For example, in T-duality, you have some other examples. I don't know the map for kappa off the top of my head there, but you can go and read the references if you are interested. But not many more examples of kappa are known. So this is something that needs to be addressed. What other examples of kappa can we of this adjustment datum can we come up with? I mean, not just any, but some kind of physically relevant examples are needed. Yeah, one can construct sort of trivial examples of kappa out of like special kinds of Lie groups, but that's not so interesting. This string example, this string Lie to algebraic example, which I showed you previously, that indeed is also physically interesting. Okay, so this is, I think, all for now. I mean, there is an example of construction, but I think I've kept you long enough, so I'm not gonna go into that. Only if you ask. But yeah, I think that's it for now. So let me just summarize briefly that yeah, higher structures are not useless, because we now have a proper definition of non-abelian gerbes with connections, and we have explicit examples. So I only gave you the infinitesimal version of those, the string Lie algebra version, but you can integrate that to get a truly, I mean, an example of a truly non-abelian gerbe with a connection in a particular case when the group is a so-called string group. Yeah, and that is related to string structures. But yeah, I think I've gone on rambling for quite some time. So I mean, if you want to hear more about this, then please let me know. But if not, then I think I'll be done for now, for today. Yeah, okay. Let me just add that what needs to be done is, as I said, construct more other physically relevant examples, and also understand the origin of the adjustment datum. I mean, so far we only had this kappa, this strange map that takes, first of all, it mixes like the Lie group with the Lie algebra, maps you into H, right? And it has to obey these two conditions. I mean, how to understand this more naturally, geometrically? What does it arise from? That's something that needs to be addressed as well. Okay, so I think that's it for now, and thank you for your attention.
Thank you very much, Dominik. That was quite a tour de force. There probably are maybe one or two questions still that have been asked.
Does this only work with continuous gauge transformations?
Indeed, yes. Yes. So I'm not sure how this relates to the discrete ones that are usually used in this other approach, this TQFT approach of categorical symmetries and this generalized, this Simon's collaboration, right? So I'm not sure. I mean, it's sure that there is an overlap somewhere. It's just at the moment it's unclear to me where it is, because they also want to be able to extend this to like continuous symmetries, like continuous non-abelian symmetries, and that is difficult because they run into the same problems. So I think in that case, our work might be useful to that program as well. I mean, I'm interested right now in understanding that better, but that's work in progress.
I was more thinking of large case transformations where they're discontinuous because of you're on like a compactified surface that you see for like spherular transitions.
Okay, yeah, in that case, I'm not sure.
Okay. And then you were talking about doing this at loop level. What if I wanted to include like thermal effects into like my quantum field theory? Would this still work here?
Well, he hasn't given us any theory actually yet, so
Yeah, yes.
Okay.
Yeah, I haven't given any particular theory. Yeah.
can you show us just one more time what your explicit kappa was for that last example?
Sure. The string example, right?
Yeah, you had. So how should I read this? You've given us a kappa hat in terms of a kappa.
Yes. So kappa gives you a loop in terms of a commutator, right? So first you.
Oh yeah. So you're just closing a loop here, right? Okay.
Exactly. Yeah. So I construct a straight path.
Mm-hmm. And
then
the second term is the integral over this.
So this is a 3 form, right?
Yeah.
So this is indeed obtained from the Katz-Moody cocycle.
Mm-hmm.
Because one realization of that. So when you integrate this Lie algebra to a string group, that involves somehow the Katz-Moody group. So the central extension of the loop group of G.
Mm-hmm.
And in that case, yeah, the Katz-Moody map, right? This cocycle, this Katz-Moody cocycle it's precisely this. It has this form.
Yes. Yeah, I was hoping to be able to see how to parallel transport these loops, and I was trying to put it on a lattice in my head as you were going along.
Yes.
But
yeah, so I haven't described this. So this parallel transport, yeah, so that's actually the parallel transport story requires the adjustment, because otherwise you again recover the fake flatness out of consistency reasons. But I mean, parallel transport that I described in the beginning, it associates to certain path some kind of element in your group, right? That's ordinary parallel transport.
I mean, I can put it on a nice square lattice, and you've got a link variable which you're parallel transporting to the next link there. Now you're enclosing an additional curvature that you can add to this.
Right. Yes.
But I
mean, putting this on lattice, first one is to, I guess, understand the continuous version, right? I mean, this can be used to formulate the continuous version, and then one can.
Yes, no, it's the continuous version that's relevant, yeah. But it's the it's what's happening for beyond the differential calculus version of it. You have to go beyond that.
Okay. In what sense?
Like well, you have your curvature on the lattice is a plaquette variable. It's the product of the ordinary one in gauge theory is the product of the link variables around the plaquette. But now you're adding to this an additional plaquette variable,
yes,
which and there's this last kappa correction is the part that I can't get in there in my head.
I mean,
but, anyway.
even without the kappa correction, you would still have some kind of freeform curvature, right?
You would, yes.
Yeah, you would. So, I mean, it's the same story. It's just that now the formula for H is different.
Yeah.
The formula for H involves also this kappa term. But otherwise, it's still the same formulation. I mean, you still associate constructing
But
this.
you see, there's a consistency between parallel transporting one link to the opposite face.
Sure.
And
Yes.
and you drew a parallelogram there. If I transport one direction or perpendicular direction,
Yes,
there's a
yes.
consistency condition, which is, I think, where your problem is arising.
Precisely. And this, yes. Yeah, I mean, that was basically the picture with strings, right? This,
Yeah.
So this is how, yeah, exactly doing this, the parallel transport in even with with this higher gauge theory. So not just because, I mean, I use this to motivate why you need to use higher categories. But one could argue that even higher categories are not enough because you really need this extra adjustment there.
Yes.
That's precisely because this would be inconsistent unless f is 0, right? Unless this fake curvature vanishes. But if you add this extra datum, you don't need this condition. So again, consistency of parallel or higher parallel transport again leads to the same condition, this fake curvature condition, and nothing else, as far as I know, is needed. No other consistency condition is needed. And this adjustment lifts this condition. So you can do the same parallel transport as I think it was already Baez, or it's definitely in this Baez and Huerta lecture notes. That he explains the story with high parallel transport. And right, and when you have this adjustment, you don't need the fake flatness as a consistency condition. You only need the existence of the kappa, right? But again, the kappa, so this caveat that I mentioned, kappa doesn't always have to exist. It exists in these particular examples that we discussed, but we are not sure if kappa always exists, like in all examples. I mean, one needs to be able to find such a structure. If one is able to find such a structure, then sure, one is guaranteed a consistent higher parallel transport.
It would be nice to have a theory, the simplest theory that you could work a little bit more with.
Yeah, I mean, yeah. For now, I mean, absolutely true. We've been working on, like, when it comes to physical theories, the string structures play a role in, as I said, when trying to formulate the 2-0 theory.
Yeah, that's not a simple theory, though.
Yeah, absolutely. Yeah, no, I agree.
Yeah.
Yeah, but anyway, that's what we've been playing with.
Right. If there are no other questions, maybe I'll stop the recording and we can, at least, because we've got a rather long recording at this point. Let's see where my...
I think Martin has a question, but
go ahead. Go ahead.
I'm guessing he wouldn't mind asking it after the recording is stopped.
I can wait a second. That's no problem. Go ahead, Martin.
When it comes to, like, going back,
we can't hear you very well.
Yeah, I can't hear you very well.
Hang on, I'll see.
I don't think your sound is working well enough, Martin, to be able to ask it. So I will stop the recording and we can.
Okay.
Is that better? Can you hear?
Yeah,
yeah, that's better. Yeah.
Yes.
Yeah, no, it's just, like, I suppose going back to the beginning, am I right in assuming that, like, if you were to just specify, I suppose, an object, you can kind of then just, follow through, and at the end you'll probably get some Lagrangian that's, so, like, say if you chose that object to be like a matrix, say, what kind of, like, is that, am I right in kind of, is that how you would sort of use?
What objects are you talking about?
So going back to when you're talking about the sorry, yeah, like I suppose the objects that are you know, you're saying the kind of in the categories you've got objects
Yeah.
transformations between them. So am I kind of right in assuming that, like, if you were to say specify an object, you know, something with these conditions where it's you know, or I suppose where there is some sort of composition, you know, the properties are as they need to be.
Yes.
What? Yeah. So how constrained is it? Can you choose sort of any object where?
I mean, in like for a category.
Yeah, for a category, if you're to like, and then if you're to choose.
Sure. I mean, I mean, category. They're just generalizations of sets, right? Just as for a set, you can choose any collection of basically objects, like anything you want, numbers, apples, or whatever. Just as, I mean, you can do the same for a category, but you have to make sure that you satisfy all the axioms of a category. And similarly for a two category. So anything can be a two category as long, anything abstract can be a two category as long as it satisfies those axioms.
And I suppose if you were to like say, you know, if you were to choose some, you know, object in, you know, maths, would you kind of get a Lagrangian out of it, or would it kind of be a sort of?
Yeah. Well, I mean, there are like natural Lagrangians, let's say, or theories, models that you can get out of these things. One of them I've already mentioned, that was this homotop. So for L-infinity algebras, which are some kind of categorified Lie algebras, right? The object, well, the interesting theories that you get was this higher gauge theory. I discussed this homotopy Maurer-Cartan theory that you get as kind of a canonical theory associated to an L-infinity algebra. So that's, I mean, and it models. Yeah, I mean that's interesting basically just for Chern-Simons, but not much else. Only topological. It's because your curvature vanishes. But other than that, you are not really constrained. This is really just developing a framework in which to view higher gauge theories, and then you are just free to choose whatever theory you like as long as it fits into this framework. But yeah, it doesn't constrain you very much. Like, doesn't uniquely specify a theory for you where this thing works.
Interesting, yeah, because I was thinking, like, it seems quite you know, straightforward, just the identity and the composition of the maps and stuff like that. So like, I suppose, you know, going back and, you know, inserting whatever, you know, object you choose into this, you could maybe, I guess, you know, I guess the idea would be linked somewhere with something that's
yeah, I mean, it constrains certain bits, but then others are left unconstrained, right? So what all these constraints give you is consistency. So when you want to talk about like these higher gauge theories, you have to make sure that your higher gauge theory is gauge invariant, right? When you write down the Lagrangian, it has to be gauge invariant. And precisely these kind of prescriptions that I showed you guarantee that. You are guaranteed a mathematically consistent higher gauge theory. And inconsistent not just in the fact that it obeys that it is invariant, but also, for example, this higher parallel transport story, that you don't run into this kind of consistency problems, that you don't not necessarily require fake flatness. Yes, but this framework is guaranteed to give you a mathematically consistent higher gauge theories. So that was, I mean, the whole point of the exercise. But it doesn't constrain the theories in any other way.
Yeah, it's interesting. Yeah, so yeah, thank you.
Stop the recording this time.